All right, we can now continue with some examples, some further examples of Fourier transform. We have seen the Fourier transform of a damping exponential, a decaying exponential, starting with u of t. We have seen the Fourier transform of an impulse, delta t, and we saw that it's one, constant. It doesn't change with frequency. Now, the next example is quite a typical one, again, which is the rectangular box. Its value is 1 from, let's say, minus capital T1 to capital T1, and this is x of t. We can also write the same thing, just for convenience. Let's indicate how to write it analytically. It's like 1 for magnitude t is less than t1 or less than or equal to, if you wish, and 0 else. So what's the Fourier transform of this one? I will immediately jump to the conclusion. I will not go into the details of the integration because the result is somewhat more important for this case. The Fourier transform is x of j omega, which is from minus infinity to infinity, integral of x of t e to the minus j omega t dt. But x of t is valid only from minus t1 to t1. So I can also indicate that the starting point of the integral is minus t1, and it goes up to plus t1. Beyond those two limits, the signal is 0. The integration will not contribute to any number. And inside it, it's 1 times, because the value of the signal is 1 times e to the minus j omega t dt. So all you have to do is to write an integral in the form of minus 1 over j omega e to the minus j omega t from t1 to minus t1 or something like this. And when you write it down, that's the place that I'm going to omit. You have to substitute omega is equal to, t is equal to t1, and then t is equal to minus t1, and subtract the second term. After some simplification, there's some cumbersome operation that goes on over there. It will simplify into this. Two times sine omega t1 divided by omega. Now, whenever you see sine x over x, you may remember that the signal is in the form of a sinc. So this is a sinc signal, which is making some crosses at some particular values of frequency, omega. So let's try to plot it very briefly. We can now plot this one because it is real valued. There's no complex or imaginary part of it. It's purely real valued. So we can essentially plot x of j omega itself, not the magnitude, but itself can be drawn. And the reason that this Fourier transform came out to be a real valued function of omega is because the original x of t is symmetric. It's an even function. Okay, then we know that the Fourier series coefficients and the Fourier transform are purely real. But what do they look like? First, let's try to substitute omega is equal to 0, and it requires a limit determination to find x of j omega at omega is equal to 0, because it's a sine 0 over 0 thing, which is a 0 over 0 ambiguity. You can use the Hospital's rule, or you may know the answer already. And it's found to be sine omega and omega, where as omega goes to 0, as the angle goes to 0, behave identically. So actually sine omega over omega as omega goes to 0 is 1. And whenever sine omega, the omega inside the sine is multiplied by something, then that directly reflects as a coefficient, just like the coefficient of 2 over there. So the peak value that we have here is actually 2t1, okay? And from there, the sinc, as we know, is reducing its magnitude and making oscillations like this. That's the shape of the sinc. Every time, of course, the magnitude is becoming smaller and smaller, etc. And there is one nice thing about the sinc shape. These crossing points are, of course, due to the periodicity of sine, therefore they are integer multiples of one another. Like there is the first zero crossing, and the second zero crossing is twice of that. So where is that first crossing? It happens when sine omega t1 becomes 0, and it becomes 0 when omega is equal to pi over capital T1, because if you insert pi over T1 and multiply by T1, T1s will cancel, it will be sine of pi, which is 0. So this happens at pi over T1. And then the next one is at 2 pi over T1. And then the other one, the next one is at 3 pi over T1 and 4 pi over T1. And this is at minus pi over T1 and minus 2 pi over T1, etc. It goes on like this. I'm drawing a little bit small, sorry for that. Let me enlarge it a little bit. So this is the sinc shape that we have. Although we will see the properties of the Fourier transform, we may start talking about the properties already. We have started talking about some observations, which I will list as property number 1, property number 2, etc. The first thing that I have indicated is that the Fourier transform is 2 sine omega t1 over omega, which is real because x of t is an even signal, a real and symmetric signal. And now I'm indicating another relatively important observation. Now notice where we start from. We start from minus t1 and go up to t1. If the width of the box becomes larger, so we are like stretching the signal to make it a wider signal, that makes t1 larger. And if t1 is larger, look at the shape of the Fourier transform, the sinc shape. If t1 is larger, then pi over t1 will be smaller, right? And 2 pi over t1 will also be smaller relatively. So if I'm stretching up my signal, I am squeezing down my Fourier transform. This sinc shape become narrower, okay? Like a squeezed version of the top one. Conversely, if I squeeze the time signal, make it narrower, it's like stretching the Fourier transform. So they behave just in the opposite directions. If you stretch one of them, you squeeze the other one. If you squeeze one of them, you stretch the other one, okay? Their shapes, width of the shapes are changing in an opposite manner. Okay, that will be an important property that we will use and see. Now, another property-like thing is an example about the inverse Fourier transform. We haven't seen any inverse Fourier transform examples yet, but this would be a good idea, and it will show us a duality property. The question is as follows: x of j omega, the Fourier transform this time, is given as 1 when magnitude omega is less than a threshold w, let's say, and 0 else. So essentially, it's a rectangular box on the Fourier frequency domain, omega. From minus w to w, it is 1, and this is x of j omega, something like this. So this time, the rectangular box shape is in the Fourier domain. And as we can see, it's the perfect or ideal low-pass filter. So what's the time domain version of an ideal low-pass filter is the question. And we can write it using the formula, but I'm not going to evaluate from the formula. I will just write down the result. The formula tells me that x of t is equal to 1 over 2 pi from minus infinity to infinity x of j omega e to the j omega t d omega. But it's not from minus infinity to infinity. That's not necessary. Only from minus w to w, x of j omega is valid, and that is 1. So I limit the integral limits to w. And inside it, it's 1 times e to the j omega t d omega. And this integral is extremely similar to the integral that I did here. Okay, they are almost the same integrals. And the results are also very similar. The result for this one is sine wt over pi t. So it's like sine t over t, which is again a sinc function. Only the scales and the angle scales are a little bit different. This is also a sinc. By the way, the proper definition of sinc is the following. Oops, excuse me. Sinc t, this is the definition of the real sinc signal. Others are just variants of that. Sinc t is sine pi t over pi t. Okay, this is the sinc formula definition. Let's keep it as it is, but nevertheless, both of the example sincs are also sinc waves. But what does it look like? Let's draw these sinc shapes. You may remember that sine of an angle and the angle itself are the same as the angle approaches to 0. So just eliminate the sine of sine wt divided by pi t. It's like wt divided by pi t as t goes to 0. Therefore, the thing at t is equal to 0 is w over pi. So let's put it here, w over pi. This is the peak value, and it makes a 0 crossing, another 0 crossing, another 0 crossing, and every time it makes a 0 crossing, the energy or the magnitude just decreases. Something like this. It goes on like this. And the 0 crossing appears when the angle w times t is equal to pi, the first 0 crossing position. And that makes w to be equal to, t, the time, to be equal to pi over w, because w times pi over w will be pi, so the angle will be pi, and sine of pi is 0. So this is pi over w, and this is 2 pi over w. This is 3 pi over w. This is minus pi over w, etc. It goes on like this. This is the sinc shape. And the same duality is also valid in terms of making one of the domains wider makes the other domain narrower. For instance, if the low-pass filter x of j omega here, if it is a wider low-pass filter which passes more of the frequencies as w increases, in other words, pi over w will decrease, therefore it will be a narrower shape. Okay, as I increase w, this sink shape will become narrower and narrower and narrower. And interestingly, from our previous example, if I make this W to go to infinity so that x of j omega is 1 everywhere, it's a very extremely wide low pass filter, which is essentially an all pass filter. It's 1 everywhere. Then what would the time domain signal be? What will it correspond to? It will be an extremely narrow sinc function, because the zero crossing pi over w will shrink down to 0. It will be very, very, very narrow. But meanwhile, the peak value, which is w over pi, will tend to infinity, because w is going to infinity. W over pi is also going to infinity. So it will be an infinitely high but infinitely narrow sinc, which is essentially the impulse. It's an approximation or the limiting case of an impulse as well. Because we know that if x of t, this one, is an impulse, its Fourier transform is 1, which is as w goes to infinity. That's another limiting way of obtaining an impulse. It can be also considered as limit as w goes to infinity, this sinc will go to an impulse. Let me write it if you wish. Limit as w goes to infinity, sine wt over pi t approaches to delta of t. That's an interesting observation that we can make. Okay, now let me open a new page. I recommend that you digest these things. I'm going a little bit fast. I'm just giving you examples and then another example, another example. And I'm aware that it may be merely possible to follow, but I'm also submitting these videos on the internet, so you can watch them again, and better yet, you just solve the exercise questions for determining the Fourier transforms. But before that, we need to cover the properties. We have to list out the properties which will greatly help us solve questions. Now, another example. This example is the critical link between Fourier series and Fourier transform of periodic functions or periodic signals, because periodic signals also have the Fourier transform. I said that if you have a periodic signal, you can have the Fourier series, and that's correct, and you have the tools for that. The way to attack the problem of determining the Fourier transform of those periodic signals is through determination of the Fourier series coefficients. For example, if x of t is equal to e to the j omega 0 t, it is a complex exponential and it is periodic. Okay, therefore, we have the Fourier series coefficients. Okay, so we will use those Fourier series coefficients to construct the Fourier transform. What are the Fourier series coefficients, by the way? The Fourier series coefficients for this one is, there's only one Fourier series coefficient. It's already in the complex exponential format. We have Fourier series coefficients, I say, but we have only one Fourier series coefficient here. And that Fourier series coefficient is A1 is equal to 1. Because this is 1 times e to the j omega 0 t. What's the fundamental frequency? It is omega 0. And at 1 times omega 0, what's the coefficient of that? It is 1. So A1 is 1. Okay. There is only one Fourier series coefficient. What you do to proceed with the Fourier transform is the Fourier transform, which is x of j omega, is determined as 2 pi times the AK, or the Fourier series coefficient value, which is 1 for this case, times the an impulse at the position of the, or at the frequency of the corresponding harmonic. So this is actually 2 pi times delta omega minus omega 0. The Fourier transform of this example is 2 pi times omega minus delta omega minus omega 0. So what is it? Let's plot it. This is x of j omega. Let's say omega 0 is this here. So it is an impulse whose magnitude is 2 pi times 1. This is the Fourier transform. So we find the Fourier series coefficient and we insert an impulse at the position, at the frequency of the Fourier series coefficient. If there are multiples of Fourier series coefficients, we have to insert multiples of impulses. For example, x of t is equal to, let's give some values like 3 cosine omega 0 t, okay? What's the Fourier transform of this? We have two Fourier series coefficients, as we know, a1 and a minus 1. They are the same because cosine Euler expansion is 1 over 2. 3 times 1 over 2 is 3 over 2. These are the Fourier series coefficients. Where are they? What are the frequencies corresponding to these Fourier series coefficients? One of them is at omega 0, the other one is at minus omega 0. So let's draw them. Let's assume that omega 0 is here, therefore minus omega 0 is here. So I insert an impulse here, and the value of the impulse is 2 pi times 3 over 2, which is actually 3 pi. And the same here, which is also 3 pi. So this is the Fourier transform as a plot. I can write it analytically as 3 pi in parentheses delta omega minus omega 0 plus delta omega plus omega 0. One of them is at omega 0, the other one is at minus omega 0, two impulses, and their magnitudes are 3 pi. This is the Fourier transform. So I'm not evaluating any integrals. I'm not doing the Fourier transform formula or anything. I'm just using the known Fourier series coefficients, and I'm multiplying them by 2 pi and inserting them as impulses. And that's it. I'm just defining it that way. A further example is x of t is equal to sine omega 0 t, for example. Of course, the Fourier series coefficients this time will be a1 will be equal to 1 over 2j, and a minus 1 will be equal to minus 1 over 2j. These were the Fourier series coefficients from the Euler's expansion. If you can do the Euler's expansion, you can use them. If you don't have them, you can just use the formula or use the methodologies that we developed for determining the Fourier series coefficients. You just have to find them. So 1 over 2j and minus 1 over 2j. The first one is at omega 0. The other one is at minus omega 0. At omega 0, let's say omega 0 is here. So this is an impulse, and the magnitude of the impulse is 2 pi times 1 over 2j, which is pi over j Interesting, but it's an imaginary number. You may ask me, why am I plotting it? And you will be correct, but just to make an illustration, I'm just drawing it like this at omega 0. And at minus omega 0, it will be minus pi over j, which will be like this, minus pi over j. So they are just inverse signs of one another. And x of j omega can be plotted like this. Now we can generalize this expression. In general, x of j omega for the Fourier transform for periodic signals is a summation, because there may be many Fourier series coefficients, over k, no matter how many. It may be infinity, it may be from minus infinity to infinity, 2 pi times ak times delta omega minus k times omega 0, which are impulses at the positions of the harmonics. The harmonics are at integer multiples of omega 0. So when you encounter a question where you have to find the Fourier transform of a periodic signal, this is indicating you that the Fourier transform will contain impulses. And the magnitudes of the impulses will be related to ak. Ak times 2 pi will be the magnitudes of those impulses. And the positions of the impulses will be at the harmonic frequencies, corresponding harmonic frequencies. The one that is containing ak, for example, the position of the impulse will be k times omega 0, whatever that k is. Okay, now I may proceed to a further example. Yeah, it's a little bit cumbersome, but we have to maybe go through this example. The example is for an x of t, which is a rectangular box train from minus t1 to t1. Okay, the example that we saw for Fourier series, and the period is capital T, let's say, or the frequency is 2 pi over capital T. The fundamental frequency is omega 0 is 2 pi over capital T. We have already developed an answer for that. We say that AK is equal to sine k omega 0 T1 divided by pi k. This was an example. This was an answer that we have developed, which is from where now I can convert it into a Fourier transform like this, x of j omega. Therefore, quite simply, whatever this ak is, I will just substitute into the equation that I draw in the box at the top that you see here now. And that is, therefore, the same k from minus infinity to infinity. This thing, ak, I will have to multiply it with 2 pi. So what is 2 pi times ak? There's a pi in the denominator of ak. That pi will cancel with the pi of 2 pi. And in the numerator, I will have 2 sine k omega 0 t1 divided by k, pi's are cancelled, times delta omega minus k times omega 0, whatever omega 0 is. It's 2 pi over capital T, just a value. Now, what do they look like for some certain choices of T and T1? For example, it's a sub-example of this. Let's say that capital T, the period is 4 times T1. So it's a half-duty cycle, positive, and half-duty cycle 0 pulse train. 1 and 0 and 1 and 0. Half of it is 1, half of it is 0. Then omega 0 will be equal to 2 pi over 4t1, which is pi over 2t1. Okay, that will be omega 0. And integer multiples of this omega 0 will be the positions of the impulses. I will just draw this as an example. We have a sink envelope. Okay, so that's why I'm drawing it to be dotted like this. Like this. And this is the frequency axis, omega. The first one will be at pi over t1. Omega 0 is equal to pi over t1. And the zero crossing of this sink shape is twice of that, because it's 2 pi over this one. So it's going to be like this. An impulse here, whose peak value is, by the way, 2. Here the peak value is pi. And this is also y. This is also an impulse like this, whose magnitude is 2. And this is at omega 0. This is 0. This is minus omega 0. This is 2 omega 0. 2 omega 0. And at that point, or minus 2 omega 0, at that point, it makes a zero crossing. So the Fourier transform is 0. And then I will have a negative thing at 3 omega 0. At 4 omega 0, it's a 0. Here, a positive one, a 0, etc. So these impulses are the Fourier transforms that we have. And some of the impulses have zero magnitude. As you see, they exactly coincide with the zero crossing of the sink. You may want to become familiar with sink shapes and when they make zero crossings, what are their peak values, etc. By solving questions and seeing example questions, let's say from the book or from other resources, because it's always a good idea to sorry about this. It's I was saying it's always a good idea to become familiar with the sink shapes and solving such questions. It will greatly help you to solve a question more quickly, let's say in an examination, or to make an inspection to the question and see what the result should really look like even before solving the questions. Now, another example. This example is also a periodic signal. It is x of t is equal to an impulse train, k from minus infinity to infinity, delta t minus k times capital T. This is an impulse train separated by capital T, which is the fundamental period, right? So do you remember what the Fourier series coefficients were? They were ak to be equal to 1 over capital T for all k's. So they were constant values for all harmonics. The Fourier series coefficients just did not change. If you don't remember this, you may go back and watch the related lecture again. So AKs are 1 over capital T. Then what is the Fourier transform? The Fourier transform is, by the way, what is omega 0? Omega 0 is 2 pi over capital T, of course. That's the fundamental frequency. So an impulse at 0, whose magnitude is 1 over capital T times 2 pi, which is 2 pi over capital T at 0. And another impulse at omega 0, which is again 2 pi over capital T in magnitude, and then 2 omega 0, etc. to the left and to the right, like this. This is x of j omega on the frequency axis. That's interesting. It is telling me that the signal is an impulse train, x of t is an impulse train, but its Fourier transform is also an impulse train. What an interesting coincidence, right? We can write analytically what the x of j omega is, and that is equal to 2 pi over capital T summation, again k from minus infinity to infinity, delta omega minus k times 2 pi over capital T, or k times omega 0, that is. This is omega 0 anyway. So an impulse train signal and its Fourier transform is also an impulse train. That's interesting. It is interesting because there is another way of solving the same question with a different answer, but those two different answers are essentially the same answers. But it's interesting. An alternative solution of the same thing is the following. Notice that x of t is an impulse train, so let's analyze each of these impulses and let's find their Fourier transforms separately. For instance, there is the delta t whose Fourier transform is 1, and there is delta t minus capital T whose Fourier transform is what? You can evaluate it if you wish. You will find it to be e to the minus j omega capital T. This will be the Fourier transform. You can just evaluate this integral from minus infinity to infinity, delta t minus capital T e to the minus j omega t dt, right? This is the Fourier transform. And this is non-zero only at t is equal to capital T. And this thing at t is equal to capital T is e to the minus j omega capital T, okay? So take this out of the integral and write it here. Then the integral will be the integral of a shifted impulse, which is the area under an impulse, which is 1. So the result will be whatever you have here, which is e to the minus j omega capital T. That's why delta t minus 1's Fourier transform is e to the minus j omega capital T. And the other impulse is at 2t, whose Fourier transform is e to the minus j 2 omega capital T, or omega 2 capital T, whatever. And it goes on like this. And then I'm summing these up to come up with the impulse train. So I have to sum up the right-hand side of the equation to come up with the Fourier transform. And that summation is, it can be written as k from minus infinity to infinity e to the minus j k omega capital T, okay, for all k. That is the summation. This is x of j omega. Let me put it in a box and let me go up a little bit and put this in a box. Okay, they are both correct answers. X of j omega you can say to be 2 pi over capital T summation of impulses, shifted impulses on the frequency axis, or summation of complex exponentials. So this is equal to this. Okay, you may say, so what? But they look very different. So that is a little bit disturbing me, and I want you to be disturbed to have a better understanding and feeling about how amazing these things are. It's so disturbing. The bottom equation in the box is telling me that x of j omega is a summation of complex exponentials. And complex exponentials are smooth sinusoids. We know it's a cosine and a j sine term. So sinusoids are very smooth functions. I'm summing up very smooth sinusoids, infinitely many of them. And at the top, what I'm obtaining is impulses, an impulse stream, shifted impulses, many of them. And impulses are the sharpest signals that you can have. So the smoothest functions, I sum them up and I obtain the sharpest function that you can imagine, which are impulses. For example, if in a mathematical Olympiads, okay, Olympic Games, they ask you to prove that this is equal to this. That you may just look at it like puzzled. What do you mean prove that this is equal to that? They don't even look similar, not far, not yet alone being equal. They look very different, but yeah, they are the same things. And the way to prove this mathematically is through the knowledge of Fourier transforms. And mathematicians also need to know Fourier transforms and complex calculus to prove many of such interesting equalities. But nevertheless, this one, the last one that we have here, is not very much used. It's not preferred. We prefer this solution of impulse train Fourier transform with another impulse train that helps us in developing formulas for sampling, which is a very practical tool to convert a continuous time signal to a discrete time signal. So in digital signal processing and in sampling, this Fourier transform of x of j omega, which is indicating that it's an impulse train, will be very much used. And you will remember, if you take that course and if you go through those discussions, you may remember that you have seen it. X of t being an impulse train will have a Fourier transform of x of j omega, which is also an impulse train on the omega axis, of course. And the duality is also still holding. If you decrease the period between the impulses in the time domain by increasing the frequency, if you decrease the separations of impulses of x of t, then it means that in x of j omega, these impulses will be separated and separated farther and farther away. Or if you are increasing the period and making the separations wider in the time domain, then it means you are squeezing in the frequency domain. This kind of a duality is a critical and important property of Fourier transforms. Now, according to my notes, we will be continuing with listing out these properties, some of which we have seen, but we may start the new week with these properties, and they will help us solving questions. In many of the cases, we will use the properties to solve questions. Otherwise, every time we see a Fourier transform, if you just put it inside the integral, that would be a headache. So we will solve questions through these properties. We will start listing them out starting next week on Monday. So we can stop at this point, I guess. And if you have any questions regarding the things that we have seen, you can ask. You can type on chat or open your mic and ask. I'll give you a few seconds if you have any questions. Otherwise, I will stop the recording and I will end the meeting and we will meet next week on Monday. And no, I haven't graded your lectures, your exam papers yet, because there are too many of you. Okay, apparently there are no questions. So I'm ending the recording and I'm ending the meeting now. Let's meet at the same place, same hour next week, Monday and Wednesday. See you then.